All right, here we go. So today we're going to talk about torque and rotational inertia. So in the last video, we talked about the relationship between rotational kinetic energy and rotational inertia. And so this section, we're going to talk about torque and rotational inertia. And as has been the case with a lot of the stuff this chapter, most of this is going to be review. But the big thing is obviously the difficulty of the problems is going to ramp up. And in particular, there's one type of problem that we have not yet learned how to solve that we need to tackle here. Okay, so I'm going to do a super quick crash course again in torque. Again, as always, if you need more than what is presented here or I'm going too fast, then please go back and watch those honors videos. Sort of the end goal here is the last video, or the last example in the video. Okay, so here we go. So as a quick refresher, so one of the first things we learned in physics was the idea that net force on an object causes acceleration, and it follows Newton's second law, right? The net force acting on an object is equal to mass times acceleration, okay? And what this means is if you want to produce an acceleration, you have to apply a net force to the object, right? Okay, so similarly, if you want to produce angular acceleration on an object, you need a net torque, all right? And then the missing variable is the rotational counterpart for mass, which in yesterday's video we learned was rotational inertia. Okay, so this is usually referred to as Newton's second law for rotation. Okay, and cool. So if you wanted to make an analogy, you would kind of say, you know, in the same way that a force is a push that produces acceleration, a torque is a twist which produces angular acceleration. Okay. So then the question is, all right, well, great. So how do we produce this twist? How do we produce a torque? Okay. Other than, ooh, I'm going to make my M. Night Shyamalan joke. Well, there, I just did. That was it. Just a twist. It's a joke. Embarrassed. There's nobody laughing because I'm in an empty room except for the people in the back of the room. Did you guys get the M. Night Shyamalan thing? Twist? Because he always puts twists in his movies, right? See, it's a funny joke. Damn it. All right. So how do you make something twist? So suppose you got, you know, whatever, this bar, and I want it to twist. All right. Well, if you want it to twist, the first thing you got to do is identify the point about which you want it to twist. All right. I usually call that P for the pivot point. Sometimes we call it the axis of rotation. Okay, either of those are acceptable. Axis of rotation is probably the better terminology for it. Okay, so the first thing, so if we've got this bar and we want to twist it, we need a force, right? But not any force will cause the bar to rotate. For example, pulling this way on the bar will not make it rotate, or pushing on the bar will not make it rotate. Okay? At least some component of the force needs to be perpendicular to what is called the lever arm. All right, so the lever arm is this invisible line that is drawn from your pivot point to the point where your force is applied. Okay, so the black vector there is my force. This blue vector is my distance, usually called lever arm. Okay, and so the torque is calculated by multiplying the length of the lever arm by the force, as long as those two vectors are perpendicular. If they're not perpendicular, then you need to multiply by the sine of the angle between them. Okay, and basically what that accomplishes is it finds the component of the force that is, in fact, perpendicular to that lever. Okay? So probably the easiest thing to do here is to just dive in and do a couple quick examples with actual numbers. All right, so here we've got this wrench. Let's say that the wrench is, I don't know, let's say the whole wrench is 30 centimeters long. Okay? So, first of all, my pivot point is going to be here, right? Because that's where your bolt would go, or your nut, or whatever it is that you're trying to tighten or loosen, right? And so, I guess let's identify that P for pivot point, all right? So first of all, notice that, well, let's do a simple example. I'm being weird here. All right, so suppose I push here with a force of 30 newtons, and let's make the length of this thing be 25 centimeters. Okay, so And assuming this is a right angle, then our torque is simply, well, the technical way to write it would be distance cross force. All right. Sorry, I'm hesitating. We went through all of this last year. So, okay. So you get 0.25 meters times 30 newtons, multiply it out, and it gives you 7.5. The units here are Newton meters. Now, here's the deal. So when we did work, we learned that work was force dot displacement, right? And it gives you the same units, all right? But the difference is this is what's called a dot product. It's a scalar product. And so the answer that you get here is exactly that. It's a scalar. It doesn't have direction, okay? So it turns out when you calculate torque, you're again multiplying kind of the same two vectors, right? There's a length vector and a force vector. But this is what's called a cross product, okay? And the result of a cross product is when you multiply two vectors using a cross product, you get a third vector, okay? So these Newton meters are actually not the same as joules, okay? All right, so, and then I guess just to be clear, I should point this out. This ruler is in my way. Get rid of it. Try to get rid of it. There we go. All right, so why do you hate me? Delete, go away, ruler. Okay, so this is the same as doing d times f times the sine of theta. Okay, and here, notice our theta is 90 degrees, sine of 90 is 1, so it still gives us this answer. Okay, now, suppose the force is at a weird angle. Well, then there's kind of two ways of dealing with it. So let's suppose our force is still 30 newtons. Oops, I'll put that there. Suppose our force is still 30 newtons, 60 degrees. All right, so the idea now is some of our force is actually just pushing in on it. That force isn't going to produce any torque, right? In this case, our x component of force doesn't actually produce torque. It's just the y component of the force that produces the torque. So, you know, you could do a little bit of trig here and find the y component. And your y component would be, what, f times, or 30 times the sine of 60, which is a number that I don't have written down because I changed the numbers from my notes, and I apologize. 30 cosine 60, so it gives you, oh, sine 60. Sorry, it gives you, it's about 26. All right, so we can now find the torque, and there's two options. Option one is, so when you find your torque, what you need to do is you need to either multiply the length of the lever arm by the component of the force that's perpendicular to it, which is kind of what we're going to be doing. You can alternatively find the component of the distance, which is perpendicular to the force. Okay, and I'll do an example like that here in a second too. Okay, and so doing this gives us, well, we're using this guy, right? So our distance is 0.25. Our force perpendicular is the 26 newtons. So multiply that out and get like 6.5 newton meters, right? Okay. All right. So that is that. And then I guess the only other weirdness that might happen is this. Just it is probably worth pointing out that a force applied here is going to give you no torque, right? Because your d there is 0. Okay? So d does not necessarily represent the length of the object. It represents the distance from the force to your chosen pivot point. Okay? All right. And I'm worried I've understressed that you have to identify where your pivot point is. And in fact, as we move forward, what you'll see is I will very frequently write this notation, net torque P. And what that means is the net torque around pivot point P. Okay? you'll see eventually we're going to get to rolling objects, and there will be times where you'll consider the center of the wheel as your pivot point, and there will be times when you consider the contact point as your pivot point. So C, oh shoot, C and contact and center both start with P, or start with C. Man, maybe I should have held off on this video today. Here we go. Center and bottom. There we go. So, you know, you might do the net torque around the center, or you might do the net torque around the bottom. Okay. So, an important thing. Okay. So that is that. Now, what if the lever arm is at a weird angle? What if I do this? What if I've got that same wrench that is still 0.25 meters and my force is vertical? Okay. Well, let's see. So if this is well, I guess we'll just do 30 degrees again. I don't like having 30 in the same example twice, but we're going to deal with it. So option 1 would be the torque is 30. So force times distance times the cosine of the angle between them. So cosine of 30 is, or sine of 30, sorry, times the sine of 30. And so that gives you a quarter of 15, which is what, 3.75 Newton meters. Okay. Now, just to make a point, this is the exact same thing as doing torque equals, instead of doing this, let's do distance times force, but let's find the component of the distance that's perpendicular to the force. So for us, that would be, all right, well, here's my distance. So draw a little vector triangle. So here's my D perpendicular, right? Oh, and that's 0.25 times the sine of 30, right? So it gives you the same answer. Okay, so you can say, oh, well, my D perpendicular is half of 0.25, so that's 0.125 times the force of 30 newtons. And it gives you the exact same answer of 3.75 Newton meters. Cool. That's why I'm asking. All right, here we go. All right, so I think everything here is stuff that we've talked about either today or tomorrow. I don't know that I need to say anything more. I guess I'll just refresh your memory. Please remember that your rotational inertia depends on mass of the object, size and shape of the object, and the axis of rotation. Again, that's a very important value, okay? That's the same as your pivot point, right? Okay, and so, yeah, this is reviewed. Newton's second laws, net force equals mass times acceleration. Oh, this just sort of derives the law, right? So check it out. Net torque, well, that's, a little t there. I don't know. So if suppose your net torque is caused by, you know, one specific force. So that force times some distance d, right? So there's your torque. Okay, well, that distance is kind of like the radius for a circle, right? So force times radius. Now if that force is your net force, then you get mass times acceleration times radius. Acceleration is just alpha times radius, right? Oh, so now we've got mr squared alpha. Notice this is just your rotational inertia, and this is your alpha. Okay, so there you go. That's your net torque. It's kind of a sloppy proof. Okay, so all right. So anyway, so like I said, this was kind of a quick crash course. Hopefully enough just to kind of get you thinking about torque again. If you need more than that, please go back and revisit those honors videos from last year, as they are definitely more detailed than what I just did there. All right, but let's see if we can apply this now to an example that was a little bit harder than maybe something we would have done last year. Okay, so what we've got here is we've got these two blocks, a 6 kilogram block and a 2 kilogram block. attached by you know, a rope over a pulley. So here's the big difference. Every time we've done a pulley problem, we've ignored the mass of the pulley. Okay, we've just assumed that the pulley didn't sort of take any of the energy out of the system. Okay, but obviously, if you've got a pulley, it's going to have some mass. All right. Now, in this problem, just to make a point, I made the pulley very, very massive. Okay, so what we're going to do here is we're going to find the acceleration of the system and the tension in the rope. And here's the other big difference. The tension in the rope is not going to be the same at both ends, okay, for reasons that I'll get to in a minute. Okay, so we've now got three unknowns. We've got two tensions, which I'll get to that in a minute, and then the acceleration of our system. And I guess technically the angular acceleration of the pulley. Okay, so let's see if we can figure out what's going on here. All right, so what we're going to do is we're going to write, for each sort of component in our system, we're going to write either a net force equals net force equation, like we did when we were doing Newton's laws, or we're going to write a net torque equals net torque equation to deal with the items that are spinning rather than moving. Okay, so that is the deal. So here we go. So let's do the 2 kilogram block. 2 kilogram block. Here we go. 2 kilograms. We're going to have gravitational force and a normal force, which I don't care about because they cancel out, and tension pulling it forward, right? Let's call that force of tension 2, as in the force of, well, we'll just call it tension 1. I'm sorry. All right, so let's do this. Up here, we're going to call this tension 1, and we're going to call this tension 2. Okay? Okay, so for this object, our net force equals net force statement is going to be, well, our net force is just force of tension 1. And our net force is mass times acceleration, so 2a. All right, so there we go. That is equation number 1. All right, now equation number 2. I'm going to do it in green. Oh no, I'm not. I'm going to do it in blue. Equation number 2 is going to be another net force equals net force equation. Okay, so for that guy, it's on an inclined plane, 6 kilograms. There's going to be an FG perpendicular and an FG parallel. Nope, that's not what I wanted to do. Sorry. Normal force. Our FG parallel is going to pull down the hill. This guy's 30 degrees, so it's just 6 times 9.8 times the sine of 30. So that gives you 29.4 newtons. And then you're going to have a tension force pulling up the ramp. Okay. So I'm going to call that force of tension 2. Okay. In a minute, it'll be clear why tension 1 and tension 2 are not the same. So bear with me for a minute. So let's once again write a net force equals net force statement. So that means, let's see, my acceleration is going to be this way. So I'm going to make it down the hill positive. So I'm going to do 29.4 minus force of tension 2 equals the mass times acceleration. So 6a. Okay, so there we go. There's equation number 2. All right. And then finally, equation number 3 is going to be for the pulley itself. And because the pulley is rotating but not moving, it's going to be a net torque equals net torque equation. Okay, so what do we know about the pulley? We know that pulley is a disc. I haven't told you yet. The pulley's a disc, all right? And so we know that a solid disc has a rotational inertia of 1/2 mr squared. So for us, that's 1/2 times 10 times, do you know what? I'm going to hold off on putting in r for a minute, and I'm just going to put r squared. Okay. So Okay, so the reason for this, the reason why I'm leaving that R in there will become clear, I think, in a minute. All right, so that's my rotational inertia. So now what I'm going to do is I'm going to write, like I said, a net torque equals net torque equation. Okay, well, so first of all, net torque is the total of all my torques. So for us, there's, well, let's do this. Let's make a free body diagram for the wheel, right? So here's my wheel, here's my pivot point. It's supported by a little thing at the pivot point, so that's not going to provide a torque. And then there's the force of tension 1 pulling this way, and the force of tension 2 pulling that way, right? Now notice, that's kind of it, right? This right here shows why the two tensions can't be equal. We know that the wheel has got to spin this way, right? And the only way that that can possibly happen is if there's more torque, clockwise than there is counterclockwise, right? So in English, tension 2 has got to be bigger than tension 1, right? Because it's got to cause that wheel to spin in the direction of tension 2, not in the direction of tension 1. Okay, so let's take this guy, move him, whoa, that's not what I wanted to do. Let's take this guy, move it over here for future reference. Okay, so our net torque, oh, well, that's the torque from tension 1 plus the torque from tension 2, and that's got to equal I times alpha. Okay, so let's do some substitutions here. So torque from tension 1, well, that's force of tension 1 times our radius, which I do think we're going to have to put it in here, but hold tight on it, plus the force of tension 2 times our radius. But notice we need to deal with our directions, right? So let's see, we know that our acceleration is this way, and we've been calling that positive, right? So let's call torque in that direction positive, so that it'll also give us a positive acceleration that way. So what that means is I want this way to be negative, which means I need to make this negative, okay? All right, so there's our net torque, and that's got to equal I times alpha. The problem is we don't care about alpha, we care about A. So what I'm going to do is I'm going to replace I with this, 1/2 times 10 times R squared. And then my alpha, I'm going to write as A over R. Oh, my R's are actually going to cancel here. Ooh, neat. I didn't even realize this when I started this example. Because when I did it the first time, I actually plugged in the radii. So this is a good argument for not plugging in your numbers until the end. All right, let's see. So I don't know if you can see what's going on here. So if we divide both sides of the equation by R, I don't know where I do it. I don't know, whatever. All the R's cancel, right? So if this becomes R times FT1, FT2 minus FT1. Try this one. Here we go. So this side of the equation here, I'm going to flip, I'm going to factor out an R, and then I'm going to write it as FT2 minus FT1. Okay? Equals, on this side, 1/2 of 10 is 5. And then I've got R squared A over R, which is AR. Oh, look, the R's cancel. Bam, kabam. All right, so now I've got equation number 3. And so now what I've got is 3 equations and 3 unknowns that we can solve, which sounds ugly, but I think it actually ends up not being too bad. All right, so, all right, so I'm going to assume people have written this down. I'm going to erase, I'm going to move. These guys over to here. Let's move this guy. Nope. That guy over there. Okay, and solve it. So what is probably the easiest way to do this? Why don't we solve, we've already got ft1 solved in terms of A. Let's solve for ft2 in terms of A. So if I rearrange this thing, you get ft2 equals 29.4 minus 6a. All right? Add, subtract, yes. So now what I'm going to do is I'm going to plug this into here, and I'm going to plug this into here, and I'm going to solve for A. And the whole problem falls apart, right? So if you do that, the green equation becomes, so ft2 is 29.4 minus 6a, so that's this. Oops, my A is really sloppy. Minus ft1, which is 2a, equals 5a. So 29.4 minus 8a equals 5a. 29.4 equals 13a. Divide both sides by 13, and a is 2 points. Something written on my paper, 26 meters per second squared. And now you can plug back into equation number 1 to find out that the force of tension 1 is 2a. So that becomes 4.52 newtons. And you can plug into the other guy to find out the force of tension 2 is 15.83 newtons. Notice bigger, just like we thought it was going to be, to provide that torque. Okay? So that is how you got to do those problems, all right? This trick of writing out a net force equals net force equation or a net torque equals net torque equation for each component of your system is the jam. All right, there you go.